Contextualized embeddings are the most recent type of representations that have addressed many of the issues associated with static embeddings like word-to-vec. As it is obvious from the name, contextualized embeddings are able to generate embeddings that are sensitive to the context. In other words, for instance, for a target word, they can generate embeddings that is adapted to the semantic or syntactic properties of that specific usage of that word in that specific context. Contextualized embeddings are one of the hottest topics of research nowadays, thanks to the huge improvements they have provided across many areas in natural language processing. So we are going to linger a bit more in this section to try to shed some more light on specific details. Here is the outline of this part of the presentation. We first start with explaining the need for contextualization, or why at all we need to contextualize our word embeddings or any other sort of embedding we have. Then we will describe very briefly this recent neural architecture which is widely used in different areas in natural language processing nowadays, especially in contextualized representation. Then we will describe how these pre-trained language models can be used for word representation, specifically how masked language modeling works. And then, among these different contextualized representation techniques, we will describe some of the earlier ones like Context2Vec and Elmo, and some of the more prominent ones recently, BERT and GPT and a few others. Then we will describe how these pre-trained models can be used in different NLP applications, specifically feature extraction and fine-tuning. And then we will represent some of the analytical works in exploring the properties of these pre-trained language models, like syntax, like depth-wise, layer-wise, multilinguality, or their abilities in doing lexical contextualization. And finally, we will conclude this part with some of the techniques for evaluating contextualized models. Let's start by seeing the necessity for having contextualization. Have a look at this word, the word time, which appears in different contexts in this example. What time is it? He called me 4 times. I didn't have time to finish. Take your time. Time of the year for planting. Time to go. Time flies. We had a good time together. So you see there are many differences among different usages here. Some of the differences are subtle, some of the differences are more major. And as you can see, the same word, and we're talking only about the noun part of a speech here and not about the verb time. And the same part of a speech can appear in many different contexts with many different meanings. So words are semantically dynamic. They can change their role, semantic or syntactic, depending on the context in which they appear. As a result of that, we need dynamic word embeddings. We need embeddings that can adapt themselves to the context in which the target word appears. So specifically, for example, for different usages of the word time, we want different embeddings that can reflect these specific usages of the word time in different contexts. In conventional models for which we had a static word embeddings, we usually had a big table of static word embeddings. The same embedding, for example, for an ambiguous word like cell. And independently from the context that we had for that specific word, we were retrieving the same embedding for the word cell and using that in our model. Obviously, this has a lot of limitations and a lot of problems. An ambiguous word like cell can have many different meanings. But we are looking for a specific meaning of cell in this specific context. We know that we can use sense embeddings for addressing the meaning conflation deficiency problem of static word embeddings. But we know that integrating sense embeddings into our NLP models involves a non-optimal word sense disambiguation stage in order to transform our words into senses. The nice thing with contextualized models is that they not only take the target word, but also their context and generate an embedding for the target word by looking at the context. So the generated embedding here can differ to generated embedding for the same word in a different context. Let's have a very quick look at the transformer architecture. The original transformer model from the Attention is All You Need paper was a sequence-to-sequence for machine translation. You have a stack of encoders for encoding a given text and a set of decoders for decoding that encoded representation into the target language. For example, here a translation from English to Italian, and the model was supposed to predict the next word. The model is basically a feed-forward model that takes all the words at the input at the same time. We will see later how the order is preserved given that there is no sequential structure to this network. Let's have a closer look at one of these encoders. In fact, encoders and decoders have similar internal structure with some slight differences. The main building block of the transformer model is something called the self-attention. So here is the internal structure of an encoder. So we have some self-attention applied to the input text and then some feed-forward elements. Let's see what self-attention is. Self-attention is in fact a new spin in the attention technique. Instead of looking at the encoded text, so for instance what we had for machine translation, in order to find the intended word to be translated now, here the attention is applied to the same input text. So while looking at a specific word in the context, you look at the other words in the context in order to see which are the most semantically or syntactically related word to that word in order to better understand that word. So for instance, when we look at the word cell, we might be interested in attending to membrane or to the field, and less interested in other words like is, noun, or other words. Or when we look at the word mosaic, we are interested in membrane, structure, or field, and we're less interested in other words in that context. Okay, let's see how specifically Z's are computed from the input X's. So here, imagine we have a context of two words, and X1 and X2 are the corresponding embeddings for those two words, the non-contextualized embeddings, and we are planning to compute contextualized embeddings Z of these two words after passing that through self-attention. For each of these words, we have a set of corresponding vectors called queries, keys, and values, Q, K, and V, that are trained during the training procedure of our model. We first compute a score for the target word, the word X1, thinking here, by multiplying the corresponding query into each of the words in our context. So into K1, into key for the first word, and into key for the second word. Then do some normalization and pass it through softmax, and the softmax value is multiplied by the values, by V1 and V2, resulting in these two vectors. And then a weighted average of V1 and V2 provides us with Z1. So Z1 is the contextualized embedding for thinking. That also takes into account a bit of X2 as well. This is how Z1 and Z2 and all the other contextualized embeddings are computed from X's after being passed through the self-attention module. As mentioned earlier, transformer model is a feed-forward network, and it does not have any recurrence to it like the recurrent neural networks in order to enable it to capture the sequential order of the input, here the input text. Therefore, we need some additional piece of information to let the model know the relative positioning of the input, the order of words we have at our input. In fact, the recurrence we have in our recurrent neural networks are kind of limiting because first of all, they are computationally expensive, and secondly that they limit our ability in capturing long distance dependencies in the context. So transformer models address this problem by combining the input embeddings, input token embeddings, by some specific encoding called the positional encoding. The positional encoding is in fact constructed based on some sine and cosine functions. There are some details why having such functions are beneficial in this situation that we're not going into details of. But here we have the generated embedding for sine and cosine for 15 different tokens in our input, and the corresponding positional encoding for each token is constructed by combining the sine and cosine embeddings. As we have below, we have the positional encoding for 15 different input tokens, and the size of the generated positional encoding here is 50. Okay, with this background on the transformer models and the need for contextualization, let's have a look at some of the techniques for learning contextualized representations. Context-to-vec is one of the earliest proposals in this branch, in the branch of contextualized representation. The initial goal here in context-to-vec was to compute better representations for the context of a given target word. The baseline we usually have for representing a context is to average the embeddings of individual words in that context. And usually it's a very competitive baseline. But the problem with that encoding is that it does not preserve the order or the sequence of words in the given context. Instead, context-to-vec used a bidirectional LSTM model, a recurrent model that is able to capture the relative positioning of the word or the sequential order of the input text. The idea here is to encode the context of a target word, which is cell, and to have the encoded representation for that context and make it close to the target word embedding, which is cell here. So here is the objective function. You have a missing word, you encode the context, and you try to predict the target word. The encoded representation for the context of a target word can in fact be taken as the contextualized representation for that target word. And that is why context-to-vec is one of the earliest models in this branch for contextualized representations. ELMO, or embeddings from language models, is a more recent model and a more prominent one. But in fact, in its idea, it's very similar to context-to-vec. Again, you have some bidirectional LSTM model to encode the context, but there are some subtle differences. So the major difference between ELMO and context-to-vec is that here you are predicting the next word in the sequence. So it's a language modeling objective in which, given a sequence of words, you're trying to predict the next word. But in context-to-vec, you had a missing word and you were trying to predict the missing word. And there are other differences here as well. So you're taking the encoded representation out of each and every LSTM layer in your stack of layers and combine them with a static embedding and try to learn the contextualized embeddings by combining all these representations from different layers. This takes us to BERT, or bidirectional encoded representations from transformers. In the past few years, BERT has been the most prominent model, not only in the field of contextualized representations, but also overall in natural language processing. Because BERT and its derivatives now have provided large improvements across different tasks and in different benchmarks. Remember that the original transformer model was a sequence-to-sequence encoder-decoder model. And the model was aimed at some sequence generation. For that specific task, it was a machine translation. How can we use this sequence-to-sequence model for language modeling? One of the core ideas of BERT was to find a solution for that, to find a solution in order to use transformers for the task of language modeling. Unlike the original transformer model, BERT is a sequence of encoders. There are no decoders in this model, so we have a stack of encoders, and the aim is to do some language modeling objective. Specifically, we have masked language modeling, MLM, which is the essential idea for transforming the transformer model into some language modeling. The essential idea here is that you mask some of the words from the input, like 15% of the input tokens, and you ask the model to predict the missing or the masked words. With this simple idea and with a stack of encoders, you can transform the original transformer model into a language modeling. But the objective is not like the conventional language modeling in which you had a sequence of words and you had to predict the next word after that sequence. Here you have some missing words in the sequence, some masked words, and the objective is to predict that missing word, which is improvisation here. As it was mentioned earlier, BERT has had a lot of derivative models in the past few years with so many variations and so many proposals for improving the original model. Note that in addition to the masked language modeling objective BERT had, it has an additional objective called the next sentence prediction, or NSP. And the task here is to predict if a second sentence can be considered as a subsequent sentence for the first sentence or not. It's a binary classification, and the objective is to learn inter-sentence dependencies by the model. It was shown by different people that NSP is not an optimal objective. So what Roberta did was to discard this NSP objective from BERT and to have some other modifications, like to train for larger mini batches and on much larger data and for longer. And this resulted in huge improvements across different standard benchmarks for the model. Another problem with the objectives of BERT is that it uses the mask token, this special token, only during the pre-training. And the symbol is not present during the fine-tuning time, which is something called the pre-trained fine-tuning discrepancy. Another problem is that the autoencoder assumes that the mask tokens can be predicted independently from each other. XLNet addresses both these problems by something called permutation language modeling, or PLM. PLM is very similar in its objective to traditional language models. So the objective is to predict one token given context. However, instead of receiving the context in a sequential order, as it was the case for conventional language modeling, PLM predicts tokens in a random order. This forces the model to learn difficult task of learning the dependencies between all combinations of words, in contrast to traditional language models in which they learn these dependencies only in one direction. Another limitation of BERT is that it suffers from something called context fragmentation. And that's because the inputs are usually fixed in size and they do not take into account sentence boundary or other semantic criteria. Therefore, the model cannot learn long-term dependencies between different pieces of input and across different input texts. The Transformer XL model addresses this problem by introducing some recurrence across segments. In this way, at any computation, the model is provided with information from the previous segments, which can be used for generating the starting token. This allows the model to learn dependencies that are beyond segment boundaries, as it was the case for BERT. XLM is targeted at learning cross-lingual or multilingual semantic spaces. XLM introduces a cross-lingual training objective. Similarly to BERT, the objective is to predict a mask token here. But the difference in XLM is that the model is asked to predict a mask token in one language by looking at the context from another language. And this multilingual objective has been shown to significantly improve the multilingual properties of XLM, especially shown in zero-shot applications in unseen languages. There are also some efforts in reducing the number of parameters in the BERT model to make the training more efficient and faster. For instance, one trick which is being used by Albert is parameter sharing. So the same set of parameters here are used across different layers. And this enables the model to do the same job with fewer number of parameters. A similar model size reduction is done by DistilBERT through knowledge distillation techniques. There are so many other alternatives and so many other models dozens of other models in the literature like T5 CTRL, BART, Reformer, different versions of GPT. Obviously, there is no time to cover all these models. Among this, we look at GPT, which is a bit different from most of these other models, given that it can be used in generative situations for generating text. And we will see some interesting demos about GPT-3, which is one of the latest models in this category. As it was mentioned earlier, most of these pre-trained models are trained for some sort of masked language modeling. And they cannot be used for generative situations in which we want the model to generate some text. GPT is one of the exceptions. GPT again makes use of the transformer neural model, but instead of having a stack of encoders, GPT makes use of a stack of decoders. In order to enable this generative objective, GPT makes use of masked self-attention instead of self-attention in order to prevent the model from seeing the future, which is something to be predicted. Given a sequence of words, here the task is to predict the next word. And that's how the objective can produce a generative model. In order to better understand the difference between traditional language modeling and masked language modeling, let's have a look at this beautiful demo from Allen NLP. And this demo is powered by GPT-2, which is a generative model as mentioned earlier. So let's try inputting some word. Trump is, the model is guessing that Trump is president, gaining ground in his own, never really going to win, etc. Or if we change is with ignores. It tries to predict the next words after the sequence, like Trump ignores the fact that something, ignores the call, etc., etc. Trump ignores the First Amendment, and so on. So it's a generative situation. But in the masked language modeling, it's a different scenario. You have a sentence, you have a context in which you have masked a word. The doctor ran to the emergency room to see masked patient, to see his patient, and this already shows that the model is sort of biased towards a male doctor here. Or another example we can have is, let's see how this predicts, how Bert predicts this. Trump is going to win this election. Oh, sorry, Bert, you're wrong. The most recent model in the GPT family is GPT-3. And this model is interesting from different perspectives. First of all, the model is really huge. It has about 175 billion parameters. And just to put that in perspective, the earlier model, GPT-2, had just 1.5 billion parameters. And the largest model we had before GPT-3 was a model from Microsoft called TNLG that had about 17 billion parameters. And obviously, this number of parameters equals to a very large training cost. In the next few slides, we are going to see a few demos of some of the very interesting applications that are powered by this generative model. So the first example is a conversation made by a human with a Conv AI agent powered by GPT-3. I encourage you to pause the video a bit here and to go through the conversation, which is continued in this slide. The model is really showing some smartness at some points. At some points, the conversation is getting sort of philosophical, and it's really interesting to see how it turns out. The second demo we have is about pattern matching. So the problem is that we input a few state names with their population, and we ask the model to predict or to guess the population for another new state we enter here, like for Michigan. And it predicts the population for that state, and same for Alaska. And the interesting thing here is that the model is not provided with any knowledge about the states, about their populations, or any relationship between these sorts of knowledge encoded. And the only thing we have in the model is about language modeling. So it also guesses the founded date for that state as well. It can also learn some summation between different numbers by just showing a few examples of how we can do this summation for a few numbers. Also, the relationship between a person's name and the employer. Or the Twitter username for specific people. Again, I'd like to stress here that there is nothing in the objective of GPT-3 about any of these relationships. The only objective we had during the training of this model was language modeling. And it is very interesting to see that the model is able to capture sorts of various types of patterns. Here is the second demo. So you provide some description of what UI you expect from the model, and it generates for you the HTML and the CSS code. So for example, you ask for a nav bar with a square logo and a sign up button in that and some other stuff in it, and it generates the nav bar for you. Or you want another section with customer analysis software, some buttons in there as well. It generates the corresponding section also for you. Or you want another section with 3 buttons as the features of this company. And it generates all those sections with corresponding thumbnails for you. Again, some of the section with some image in it. Another placeholder with that title deep API integration. You want a section for testimonials. And it nicely generates that section as well for you. You want also a customer section with a headline trusted by, and the customers are Twitter, Airbnb, OpenAI, and other companies. And it nicely also finds the logos of those companies for you. And what makes this very interesting is that we have not provided, again, just to insist, we have not provided anything about HTML code generation or about UI generation to the model. And all these pattern matching and all these generations are done with the objective of language modeling we had. Let's have a look at another example, the example of generating a query by just providing a description. So you provide a query like how many users have signed up since the start of 2020. And it generates a SQL query for you nicely, where the created ID is larger than the 1st of January 2020, or the average number of influencers each user is subscribed to. And it also nicely does that for you. It also groups that by user ID and average subscriptions per user. That's the criteria. You can also ask the model to generate Keras code for you, to build a classifier that classifies images into 5 classes. The input has 25,000 images of 500 into 500 dimension. And it generates the code for you. It imports some libraries from Keras. Then it has some dropouts, a stack of convolutional and pooling layers, and some optimizer and a compilation at the end. This is, at least by the look of it, it looks like a relevant code for this task of image classification. So far we saw how we can use language models for word representations, or how we can use language models for having contextualized word representations, in fact. Let's see the different techniques we can make use of these pre-trained language models in different NLP applications. In fact, the ideas here are very similar. In fact, they are the same ideas we have in other areas like computer vision. In fact, the figure I have here for illustration comes from computer vision, where you have a convolutional base, you have some pre-trained model for doing some image classification, and then you use this model in different scenarios for other tasks. So for the case of pre-trained models, we have a language model here, like BERT, that is trained using some pre-training objective, like the mask language modeling. We can use this pre-trained model in two different ways, either by extracting features or by fine-tuning that model on a specific other tasks in natural language processing. In feature extraction, we do not touch the parameters of the model. They are in fact frozen. We just add on top of that pre-trained model a new classifier that takes the encoded representations of the input and does some classification or some other task. So in this case, in feature extraction, we just use the model as a feature extractor. However, in fine-tuning, some of the parameters in the model are also trained, or in fact they are fine-tuned based on the target task. It's not only that the target classifier, which does the target task, is getting tuned during the fine-tuning to that target task, but also some of the final layers of the model, like a few last layers of the BERT model, are also tuned in order to update parameters so that they can better represent the target task. So these are the two ways we can use pre-trained models, not only in natural language processing, but in many other areas like computer vision, which are in fact feature extraction and fine-tuning. Contextualized models have shown great potential in a wide range of NLP applications, either semantic or syntactic. Also, the possibility to fine-tune these models and directly use them in various types of downstream NLP tasks shows that they kind of encode various sorts of syntactic and semantic knowledge. However, similarly to many other deep learning models, they are like black boxes. It's not clear how they function and how can they be so effective in different areas. Therefore, it is necessary to do some analytical studies in order to better understand these models, their effectiveness as well as their weaknesses. In this line, there have been many research going on something called probing experiments that can check the effectiveness of transformer-based models on various tasks. Probing usually involves checking if a simple linear model can correctly predict a linguistic property like syntactic or semantic based on simple representations drawn from the model. High performance in this prediction task is often taken as evidence that the relevant information is encoded in those representations. Earlier, we talked about the self-attention mechanism in BERT and in transformer models. In fact, BERT makes use of multi-head attention in that it allows the model to learn different patterns of self-attention. So, for example, the BERT-based model has 12 layers and each layer has 12 independent heads for learning independent patterns of self-attention. And given that self-attention is a key feature in transformer-based models, analyzing their behavior can be very interesting. And it is crucial if we want to understand how these models work to analyze the behavior of self-attention and this multi-head attention mechanism of these models. There have been many studies with this respect on multi-head attention mechanism of BERT. And one of the interesting findings is that the BERT model, even the smaller version, which is called BERT base, is heavily over-parameterized. In other words, different attention heads encode redundant information. The conclusion is coming from the observation that many repeated self-attention patterns are occurring across different heads. So for instance, here is a figure on machine translation powered by some transformer-based sequence-to-sequence model by Vojta et al. And here is the number of retained heads in the model. So you start with 48 self-attention heads, and you reduce them to 2. And as you can see here, even if you drop about half of these attention heads, still you are preserving the original a level of performance by the model. And it clearly shows that many of these attention heads are redundant, such that disabling them does not harm the overall performance of the model in open subtitles, and it slightly reduces the performance in WMT. Another study by Pilehvar et al. In 2019 showed that if you disable some heads or even some layers, it does not necessarily result in performance drop, and sometimes, interestingly, it can result in performance improvements. So for instance, here we have 7 different tasks, and the orange line here is the baseline, where you have not touched any of the heads. The darker colors here correspond to larger performance than the baseline. So we can see here that among the 12 layers and for the 12 attention heads we have for the BERT base, in many of the instances, disabling the corresponding head results in improved performance. There have been dozens of probing studies on checking the syntactic abilities of BERT and its derivatives. A prominent proposal is by Hewitt and Manning in 2019, where they proposed a probe in order to investigate the extent contextualized models encode human-like parse trees. For this, given a phrase or a sentence, they learned a linear transformation of the contextualized embeddings. A minimum spanning tree was then taken from these transform representations in order to estimate a parse tree. And the results were very surprising. The authors showed that the obtained parse tree resembles the syntactic parse tree to a very good extent. And this is interesting because it clearly shows that even though the contextualized model was trained with some language modeling objective, like the mask language modeling, they have implicitly encoded the syntax of a language, since maybe indirectly it helps them to better fulfill the mask language modeling objective. In a follow-up work, they extended this analysis to the multilingual setting, and they showed that subspaces of the multilingual BERT model recover syntactic tree distances in languages other than English, and that these subspaces across different languages are kind of shared. Another interesting analytical study on syntactic properties of BERT is by Ettinger, who showed that BERT is unable to effectively encode the meaning of negation. For instance, have a look at these predictions suggested by the large BERT. A hammer is a hammer, but at the same time the model says a hammer is not a hammer. Or similarly, a hammer is an object. Again, a hammer is not an object. So it looks like that the BERT model is not sensitive to negation. There have also been many analytical studies that check the depth-wise information that are encoded in different representations of these transformer models at different layers. One of the earlier analytical studies here is by Peters et al., who showed that the learned representations differ in their properties at different depths of the network, such that the initial layers tend to encode only high-level morphological information, whereas the middle layers tend to encode syntactic properties, and the top layers tend to encode some sort of semantic relationships, such as the co-reference. The same observation was made by Taher et al. On many other different tasks on the Sentinel benchmark. So here again, the hierarchy of linguistic information from surface features to syntactic and then semantic. So for example, in surface level sentence length prediction, these are the first layers that are performing better, but in some of the syntactic tasks like B-shift or top constituent, some of the middle layers are doing better, but in semantic tasks like SOMO or coordinate inversion, the last layers are doing much better than the initial ones. So again, the same hierarchy of linguistic information is distributed across the depth of the network. A similar observation was made by Raganato et al. On the task of machine translation. Tenney et al. Also carried out another interesting analysis on BERT's layers, and they showed that they different layers of BERT kind of resemble an NLP pipeline. This analysis showed that the different layers of BERT encode different tasks in a natural progression from basic syntactic information to high-level semantic information, from part of speech tagging to some syntactic tasks like dependency parsing, and then to some semantic tasks like semantic role labeling and co-reference. As it was mentioned earlier, the XLM model is trained with some multilingual objective, and for that, the resulting multilingual space is very good for zero-shot cross-lingual transfer. But it is interesting that even the multilingual BERT with no such multilingual objectives has very good zero-shot abilities. And this holds good even for unseen languages for which we do not have much of an overlap in their vocabularies with the training data. With respect to multilinguality, Singh et al. Observed that the model partitions representations for each language rather than having a common shared interlingual space. So for example, in this figure, the figure demonstrates all languages combinations tested, the summary representation or the CLS token, for semantically similar inputs translated into multiple languages. And it shows that at the initial layers, these representations across different languages are more similar to each other than when we go deeper in the model. And this shows that as we go deeper in the layers, the model does not abstract semantic content disregarding languages. In another interesting observation, Pierce et al. Found that in a task like NER, while the performance using the English BERT depends directly on the word piece overlap, the multilingual BERT's performance is largely independent of the overlap. So here we have the average overlap, and here we have the performance. In the English BERT, it is highly correlated, but for the multilingual BERT, there is a small correlation. This shows that multilingual representations learn something much deeper than simple vocabulary memorization. In another interesting study of the multilingual abilities of these models, Arteshte et al. Found that monolingual models indeed learn some abstraction that can be generalized across languages. In fact, they showed that multilingual representations in multilingual BERT do not necessarily rely on the shared vocabulary, and that this joint pre-training of the model is necessary for comparable performance to cross-lingual models. And for this, what they did was to train a model on the English language on L1, and then to continue the training with freezing all the parameters of the transformer model, just to continue the training in order to learn a new token embedding matrix for the new language, L2. And then again, they did some fine-tuning on the English language on L1. And finally, the embedding matrix of the fine-tuned model was swapped for L2. So this process involves no joint training, and there is no shared vocabulary, given that separate subword vocabularies are used for the two languages. The importance of lexical overlap was also investigated by other researchers with similar conclusions that the lexical overlap between languages plays a small role in cross-lingual success in these multilingual models. Most of the analytical studies or probing evaluations have been carried out on syntax and multilinguality, and there are fewer works on semantic properties of these models. So here you can see a visualization of contextualized embeddings for the word paper. And as you can see clearly, the different usages of the word are clustered in different subspaces of the space. So for example, here we have sentences that use the word paper as a material, like written without pen and paper, or paper as a medium for drawing. Here, there are some instances in which the paper is used as newspaper, and here are some examples in which the paper refers to the scientific meaning of the paper, like the paper challenged astronomers or described his experiments in a paper. Similarly, Conan et al. Showed in 2019 that The same clustering of semantic properties of words or lexical contextualization can happen not only across languages. For example, here is the word die in some German context, and here are the same word in the English context. Not only across languages, but within the same language. Like here you have a playing die. Here, interestingly, you have the verb die as a single person dying at the left side and a small cluster on the right side on multiple people dying. So this wraps up our very quick introduction to some of the analytical studies that are being carried out on investigating the properties, the weaknesses, and the reasons behind the effectiveness of pre-trained language models that are usually based on transformers. Before I conclude our discussion of contextualized embeddings, let's have a very quick look on two of the evaluation benchmarks that are widely used for evaluating contextualized models. The first benchmark is called the glue benchmark, which involves many different tasks like sentiment analysis or paraphrase detection or semantic textual similarity between two pieces of text or some textual entailment, etc. And as you can see, most of the models at the top of this benchmark are some sort of ensemble models that use BERT or some of its derivatives. A more recent benchmark is called the superglue benchmark, which compared to glue benchmark has some more challenging tasks. So for example, we have a question answering task here, a Boolean with Boolean answers, or some reading comprehension models, or again, textual entailment is one of the tasks that is repeated. And we have some Vinograd schema challenge and some other NLI-based tasks. So this word in context or the WIC task is proposed by the presenters of this tutorial, and it's a task in which an ambiguous word is presented with two different contexts, like bed is presented with two different contexts. And the task is for the model to decide if the usage was the same across the two contexts or was it a different meaning of the target word being intended. And this concludes our discussion of contextualized embeddings.